Y8 Oscillations Revisited. In the previous semester, we have studied simple harmonic oscillator, damped harmonic oscillator, and driven damped harmonic oscillator in association with the resonance. So it is a very important concept when we study electric circuit. So even though you know this problem very well, it is the last time to review everything before we go ahead. First of all, simple harmonic oscillator has the equation of motion. And actually the differential equation has been created by this simple problem. The origin of this equation is F equals ma. F equals ma, double time derivative. And when the restoring force is linear, is proportional to the displacement from the equilibrium position, and it is opposite. You know, the spring constant and mass are positive definite, so K over M, we define this one to be omega 0 squared is a positive definite. We know the sinusoidal function satisfies this differential equation. And more fundamental way of solving this problem is to multiply the velocity. In that case, you will find this is the total differential of something. What's that? If you multiply 1/2, then 1/2 x dot squared plus 1/2 omega 0 squared x squared. This one is constant. Why? If you take the derivative, this one is x dot, x double dot, and omega 0 squared x dot. Because it's a constant, it is 0. Aha. Then you will find that why don't we introduce omega 0 x-axis and x dot axis? In two-dimensional plane, it is a circle. And circle is always parameterized by some r cosine and r sine. That's it. So you don't have to learn differential equation to solve this problem. The high school student knows very well about the circle. That's it. And finally, you will find the answer can be parameterized in either sinusoidal function or an exponential function. The mathematical structure of this one is actually in exponential function, its derivative is itself. Exponential doesn't change the sign after taking the derivative. And actually, nth order derivative is itself. Very strange function. Unlike the exponential function, sine or cosine, they have a little bit different structure. Sine, double derivative of sine flips the sine. Double derivative of cosine flips the sine. That's the reason why it is a solution to this. However, exponential function, if you substitute exponential function, then you will never get the answer. Nevertheless, if you attach a parameter A, it is possible. If you attach a parameter A and put time, if you take the derivative, then you will get nth order derivative, you will get a to the n and e to the at. What happens if I substitute n equals 2? Then you will get a very simple equation. A squared plus omega 0 squared equals 0. If it is a constant, positive constant, it can be identified as a radius and it will be a circle. What's that? Your answer is a middle school student know when they learn quadratic equation. The answer is a plus minus I omega 0. Haha. So sinusoid function and exponential I theta style, the complex variable, the exponential function, they are actually equivalent. In addition, the differential equation gives a very strong constraint. I don't know whether you learn in mathematics class or not, but it is a very trivial problem many students overlook. Double derivative is itself, but why don't you take another derivative? Triple derivative also satisfies the same equation, but now it is replaced with the first order derivative. I believe now you are familiar with the Taylor series expansion, and a relatively recent approach of solving the differential equation is developed by Frobenius. Is very light in comparison with any other people. Frobenius introduced an idea: if we are solving the equation for depending on time, he assumed that the solution has analytic, that is we can take the derivative to any order. In that case, we can make a Taylor series expansion. And for example, A0 constant, A1 T1, A2 T2, and so on. For simplicity, you can put 1 factorial, 2 factorial, something like that. This is a Maclaurin series, Taylor series expansion about t equals 0. According to these relations, you will find every even power and every odd power, they are in the same class. That's the reason why the first constant, this first term, constant, determines every terms of even powers. And this one determines every term of odd powers. These two decisive constants are called this kind of equivalent to this kind of two independent parameters that are to be determined, for example, by making use of initial condition. Okay? So mainly, you have to find two independent solutions. Independent means, linearly independent means that these two cannot be 0 except for setting two coefficients 0. So, for example, y equal x, y equal 2x, these two straight lines are linearly dependent. However, y equal x and y equal x squared, they are not linearly independent. Their sum, after multiplying by any constant, it will never be 0 except for the case x plus x squared 0 times 0 times. This is the only solution for this. So what you have to find out is a two linearly independent solution for this if the highest order of derivative is 2. And in mechanics, in physics, F equals ma, F is double derivative. So what you have to do is just a second order linear differential equation. There are a bunch of formulas. I don't ask you to memorize everything. However, this one shows it looks very complicated. The finite structure is very simple. The only difference is a sine has a positive, this is a phase. Phase, moon has a different shape, sometimes in this kind of shape, sometimes full moon. This is change in the shape. When we return to the same shape, this 28 days, it is called 2 pi. And depending on the day, you will find a different shape of moon. It is called phase. And the sinusoidal function has a phase constant. However, the phase constant for sinusoidal function for sine and cosine are different. But the origin is, when you sum cosine and sine, cosine, sine, sine, cosine, we have a positive sign on it. When you consider the cosine function, cos, cos minus sine, sine, that's the reason why this negative sign appears for this. It looks irregular, but at the end of the day, you will find the rule of using the sine rule of the phase is unified for sine, cosine, and exponential function. So these are trivial examples you can train by yourself. Kinematic variables. In the previous page, I told you this is a power supplied to the system, and whatever power is computed, the kinetic energy and potential energy, their sum is always the same. This is conservative force because its curve is vanishing. So you substitute this set, any kind of set, you will find the same result. These are 3 different representations. However, the final result should be always the same. Sure, after translation, any cosine function can be overlapped to sine function and vice versa. Using the solution, for example, if you use a cosine solution, substitute this one to compute the potential energy and kinetic energy, the phase dependence appears in each contribution, but some of them you will find sine square, cosine square sum, and that is always conserved. The graphical representation for time dependence of the energies are shown in here. Damped harmonic oscillation is not conservative. Why? Because of damping force. Why don't we compute the power x dot f due to damping force? You will find minus b, that is positive coefficient, multiply the velocity squared. Real number squared is positive definite, so it is always negative. So because of damping force contribute to the system is an energy dissipator. The system loses its own energy because of damping. That makes the system complicated, but in reality, if you open the door, it will stop. Without friction, we cannot stop. Without friction, we cannot write something. It will slide. My pen will slide. I cannot grab my pen. So it is sometimes it is uneasy, but it is a natural phenomenon we have to accept. So presence of this damping term makes it mathematically complicated, but it is quite interesting to study. We again rescale this equation by dividing by the mass. Again, gamma is a positive number, and natural frequency, the characteristic frequency of the simple harmonic oscillator, square root of k over m, is again positive. The solution of the damped harmonic oscillation, if you learn mathematics, in the differential equation, their trick is just substitute the exponential arbitrary parameter multiplied by t. Then substitution will give this kind of quadratic expression multiplied exponential function. An exponential function can never be zero in any case, whether lambda is real, imaginary, pure imaginary, or complex number. It is always non-zero. So it is solving the differential equation is equivalent to solve a quadratic equation. And middle school student can solve this quadratic equation whose solutions are given like that. The problem is that the discriminant has a positive, negative, or zero. There are three cases. If this discriminant is negative, it results in exponential I omega prime t style. So we know this exponential I something is equivalent to sinusoidal function, sum of sines and cosine. This factor originates from the damping. This is always gamma is a positive definite. So your solution can be factored out to have this kind of exponentially decaying factor. Exponentially decaying and oscillate, that makes this kind of usual solution that is called underdamped. If the sign is a positive, you do not have pure imaginary part. If you do not have imaginary part, it is a real number always. That means it is always exponentially decaying, even though there are two, but you know, square root inside. This guy, the same thing squared, but subtracted by positive number. That means gamma, this one is always greater than this, in case this is a positive. Therefore, there are two kinds of solutions, this guy plus or this guy minus. However, it is always negative definite. So it is still decaying. So it is called, there is no oscillator in motion. We call it overdamped. In between, we have a double root. In that case, it becomes a zero. We have a single solution. However, this is not the fact. You have to find two solutions because the second order linear differential equation. But if you learn differential equation class, you have to learn further to find out the second solution, but that second solution can be obtained in a trivial way if you study the checkpoint. That is equivalent to find this solution. In x sub t, I have factored this y, this common factor, and because it is vanishing, and you will find the equation of motion of y is nothing but this. And this is a very trivial problem. What's that? The solution is C1 plus C2t. So high school student can solve this. They do not say it is a differential equation, but fundamental feature of the second order linear differential equation comes from very trivial problems. So just like when you learn quadratic equation, every quadratic equation is equivalent to fall down either to this, or this. Okay, that's it. If you know how to do that, how to solve these kind of trivial problems, you are able to solve this. It looks complicated, but actually becomes very simple. So underdamped motion has this kind of shape, position, and energy are being dissipated. Overdamped motion, it is a, this guy is positive, and this one is positive and less than 1. It is a square root 2 omega 0 over gamma square. This is between 0 and 1. So this guy is always less than, this guy is always, magnitude of this is always less than 1, less than this leading term. So we use this overdamped motion in lower damper in many places when we want to stop the system as soon as possible. In overdamped case, there is no oscillation because both solutions are exponential. Two exponential functions can always be expressed in terms of cosine hyperbolic or sine hyperbolic, just like the case for cosine theta and sine theta. They can be expressed as e to the I theta plus minus plus minus. So something like that, they are equivalent. If you learn a little bit more, then, and actually you can find the solution of this by making an analytic continuation if you learn a little bit about complex variable later. Critically damped motion, I propose the method, reparameterize the solution because we know this factor already. In that case, I told you it was y, but in this note it is a c. C satisfies this trivial equation. This trivial equation gives a solution, and I substitute to find that the general solution for the critically damped motion is given like that. Because of t, this is exponentially decaying function. In case C1 is a non-zero, you have linear function. If you multiply these two functions, you will find a bump. This is a typical nature of critically damped motion. But if this, in some case, this one disappears, then there is no way to distinguish this with the, not no way, it is very difficult to distinguish this this critically damped motion with the over damped motion that does not have any bump. Driven damped harmonic oscillation. This is a case, we have a driving force. You know very well now how to solve this equation equals 0. But there are two linearly independent solutions. Multiply two constants and add them up to find the general solution for equals 0. That is called homogeneous equation. Now we'll have right-hand side non-vanishing. You have a specific solution that is called a particular solution. If you know a single particular solution, then add this one to the general solution of a homogeneous equation solution to find the general solution for the driven damped harmonic oscillation. Whatever case, it is cosine, sine, or exponential, the method of solving the problem is the same. Homogeneous equation means the right-hand side is 0, no driving force. You know how to solve this one in classifying into three kinds of cases. Now we are interested in the particular solution that satisfies the right-hand side. In fact, if you turn on a system, from the circuit or TV or any electronic devices, suddenly when you turn on or turn off, there's a big change in the system. Actually, this one is originated from the solution of the homogeneous equation. So if you turn on and off many times, large amount of current flows, so the electronic device becomes out of order frequently. So anyway, this is called the transient effect. Transient effect is evanescent. That means decays, and it reaches all of the solutions reaches a uniform solution that is called a single particular solution. We say these are steady state. So when t goes to infinity. Infinity doesn't mean mathematical infinity, but just a relatively large time scale. How to find a solution? Transient effect comes from the homogeneous equation solution. What we are interested in is just insert a sinusoidal function with the same frequency as the frequency on the right-hand side that is a driving force. If you do not substitute the same frequency as that of the driving force, the sinusoidal function on the left side and sinusoidal function on the right side, driving force or frequency and omega different. If they are different, left-hand side, right-hand side can never be the same. Here, I used the exponential solution to equate the left-hand side and right-hand side. I used the same frequency. Instead, I have introduced additional phase. The reason is that this is the term coming from the gamma x dot. If I substitute the exponential function, e to the I omega t's time derivative will bring in the pure imaginary part. That makes this a real number plus imaginary number. That makes a phase shift. That's the reason why I have inserted. You know, right-hand side is independent of delta. So my solution has acquired non-vanishing phase. However, that phase dependence must be canceled by this. So I hope this one contains e to the I delta, and this one has e to the minus I delta. Multiplication will give 1. That is independent of delta. So that is our plan. And that is the fact that the cancellation requirement will give this one a plus p I can always express as it's a modulus and cosine delta plus I sine delta style. So what's that? This is e to the I delta. That makes an exact cancellation. So if I use this one, then I can determine that this phase is nothing but this delta prime must be the same as delta for the trial solution. So in such a manner, we can find the phase dependence. And this one is not only used for the exponential style, but also can be applied to cosine and sine. And it has been considered seriously in the checkpoint problems. So the amplitude, our next concern is amplitude. And amplitude has this kind of factor. What's that? The real part squared and imaginary part squared. Real part squared, imaginary part squared, and sum them up and take the square root and divide this one. Why? We had amplitude. Amplitude multiplied by this guy is the solution. So amplitude can be obtained by dividing both sides by this number. As a result, we have a graph depending on the damping coefficient and the driving frequency. We have a bump. You have a bump. This is a smooth bump and sharp. This is a width, and this is a height. This height increases and width decreases to make a sharp peak. This is called the resonance, and the resonance is magnified as gamma decreases. And the point at which this resonance appears is very near to the characteristic frequency. When you ride a swing, it has its own frequency, omega 0. And if you apply a driving force, when it is very similar to the original oscillation frequency, then you can ride it with a large amplitude. That is called the resonance. And if you turn on a cell phone and communicate with somebody else, and if you turn on TV, everything makes use of resonance, of using very small signal, amplifier, magnifies the amplitude with mechanism of resonance. So you should know this one very well. In mechanical system, it is this resonance appears slightly different from the value. It's not exactly the same as omega 0, but when we study electronic devices, we are more interested in, this is the case for the displacement. But if you consider the velocity, the velocity has a different nature. We have a omega in the numerator. In the case of velocity, that resonance appears exactly the same as omega equals omega 0. This one appears in the displacement, and this one appears in the velocity. And velocity in a circuit, velocity is a current, and this is a potential. So it is easier to control current in electric circuit. So we prefer to use velocity's resonance formula rather than the displacement in when we study electric current flowing inside a circuit. That's it.